Hello, Chem II, and welcome to the fifth video in this series on Chapter 3, Stoichiometry. We've already focused on the mole, mass relations, and then mass relations in reactions. We also did a little bit on quantity to quantity relationships in reactions. Now we're going to kind of bring it all together. We're still in Section 3, which is mass relations, but we're going to extend our thinking outside of the simple mass to mass, mass to mole to mass, blah, blah, blah. We're going to look at what is called a limiting reactant. And for that, I want to go back to what we were doing before, do a couple quick examples of what we were doing before very, very quickly, and then kind of pull it all together. So we've used this visual as our springboard, our keystone to trying to do these problems and going from anything on the left-hand side to anything on the right-hand side. So let's look at an example we haven't done that we could probably be kind of interesting. So it says, what volume of CO2 is produced at STP when 4 liters of oxygen at STP reacts with an excess of benzene? So we know the amount of oxygen, and we know that the benzene is in excess. So we do have a balance equation. We know we have the amount of oxygen we need. We're asked for the volume of CO2. So a way to do this might be to go from volume to mole to mole to volume. But that seems to be a little excessive, because if I look at my chart and considering both of my quantities are at STP, I could just do a single step. And I could do a single step from mole to mole. Sorry, from volume to volume. So I'm going to make this a little bit easier. And instead of doing this, I'm going to simply just make it a volume to volume. So I'm going to figure out what I need to go between the two. And what I need to go between the two is to look at the volume ratio from the balance equation. Oxygen has a 15. Carbon dioxide has a 12. So I have a 15 to 12 ratio. Kind of weird, but that's what it is. So I can do this in one step. I start with 4 liters of oxygen. I do a 12 to 15 ratio. And I find out that I could create, if I had 4 liters of oxygen and an excess of benzene. Okay, I have my 4 liters of oxygen. Let's see if we can get the pen to work today. Nope. Hello, pen, work. There you are. Okay. I have 4 liters of oxygen and an excess of benzene. I could create 3.2 liters of carbon dioxide. Let me try a little bit of an extension. You saw that when it quickly flipped the next one. Extension. Let's deal with this same exact equation, and let's flip it around a little bit. Let's ask ourselves about the carbon dioxide again, but this time, what if we started with 1.75 grams of benzene and we had an excess of oxygen? So now what we have is an excess of oxygen, and we know the amount of benzene, the 1.75 grams of benzene. We know the amount of benzene this time. So we're still asking for the same thing, still asking for the volume of carbon dioxide. And very similarly to what we did in the previous video, we're going to go using our flowchart from mass to mole to mole to volume. We're going to do it a series of steps. So I'm going to break this down real fast and start extracting some information. So to go from mass to mole for benzene, I need the molar mass of benzene. So that's 78. To go from mole to mole of benzene to carbon dioxide, I need the ratio of 12 to 2. And to go from moles of carbon dioxide to volume, for that I need the 22.4. So I have these 3 conversion factors. I just got to use them in the right order. So I'm going to start with what's given to me, 3.75. I'm going to use the first conversion factor, but I'm going to flip it upside down to get the grams of benzene to cancel. Then I'm going to use the second conversion factor. And again, I want to get the benzene to cancel, so I'm going to flip that one upside down too. And then finally, I want to get the moles of carbon dioxide to cancel. So for the third one, I'm just going to write it exactly the way it is. So my moles of carbon dioxide cancel. And I find that I can make 3.01 liters of carbon dioxide. So why did I do this? Well, in one example, I knew the amount of oxygen, and I tried to figure out the amount of carbon dioxide. In the other example, I knew the amount of benzene, and I figured out the carbon dioxide. What if I knew the amount of both? What if I knew the amount of both? What would I do then? Well, I always use it as an example of how to do this. And I often think in terms of an analogy. Suppose you were in a bicycle shop and you had in your bicycle shop, and for the record, you build tricycles. You have 10 frames, 27 wheels, 25 handlebars, 15 seats, and 22 pedals. Okay. So just to be the nerd I am in my bicycle shop, this is my instructions for how to make a tricycle. I take one frame, 3 wheels, 1 handlebar, 1 seat, and 2 pedals. And I want to know, based on my materials, how many tricycles can I make? So take a second to think about this. I'm going to pause. If you need to pause the video, think about it. How many tricycles can I make? So I don't know about you, but this is what I thought. I thought, well, wait a second. My 10 frames, I need 1 frame per tricycle. So I could make 10 tricycles. With the wheels, I need 3 wheels per tricycle. So I could only make 9 tricycles. Handlebars, I only need 1 of those. So I could make 25 tricycles. Seats, I only need 1 of those too. So I could make 15 tricycles. And then pedals, I need 2 of those. So there's 2 pedals per tricycle. So I could make 11. And then, again, what I thought was, let me grab the smallest number, 9. Because once I've made 9 tricycles, I have no more wheels. I have limited the amount of tricycles I can make based on the number of wheels. If I had more wheels, I could make more tricycles, but I don't. So what we're talking about here is this concept of what's called a limiting reactant. All the pieces that are in my store are reactants, kind of. They're all pieces that are needed to make the reaction, the creation of a tricycle, occur. It is going to be whichever reactant part gets used up. You're done with it. You're out of them. And once that is done, your reaction stops. And you can see by our process of how we figured out what's what, that our tricycle, our limiting reactant was the thing that gave us the smallest number in the product. So that's what a limiting reactant is. So let's look at our example here. Did I hit the wrong button? Maybe. Oh, I went to one below it. Okay, so let's look at our example. Here's our example. Okay, it says we have 4 liters of oxygen and 1.5 grams of benzene. Just like the bicycle analogy, what we're going to do is essentially think about every single reactant and how much product could we make. And we already did both of those. With the 4 liters of oxygen, we can make 3.20 liters of carbon dioxide. With the 1.75 grams of benzene, you can make 3.01. So we have 2 different numbers. What did we do with the tricycles? We picked the smallest number. So what we're going to do is say we can only make 3.01 liters. What that means is when this reaction is done, we're going to have none of the benzene left over. We're going to have no benzene left over, okay? Because benzene is the limiting reactant. It's going to go away. We're done with that. When we're done, there's no more. But there's going to be some of the oxygen left over. Some of the oxygen is still going to be sticking around. So the question would be, how would we figure out how much oxygen is left over? And for that, I'm going to go back to my tricycle analogy and ask you a simple question. When I'm done, how many pedals do I have left over? I know that sounds kind of weird because we're talking about tricycles, but how many pedals do I have left over? Well, here's what I'm thinking. I can make 9 tricycles. So with 9 tricycles, I need 18 pedals. But I had 22. So I start with 22, and I end with 8. I needed 18, so I'm going to have 4 left over. I'm going to have 4 pedals left over. That same exact process is what you're going to use in the chemistry world to figure out the amount of excess. So in order to figure out the amount of excess, we're going to take the amount of carbon dioxide we can make, 3.01 liters. And we're going to find out how much of the excess reagent, oxygen, we need. So it's a 15 to 12 ratio. We need 3.76 liters. We need 3.76 liters of oxygen. If we need 3.76 liters of oxygen, and we started with 4.00, when this reaction stops, we're going to have 0.24 liters of oxygen left over. Limiting reactant. Now, let's see. We got a reaction that had benzene reacting with oxygen. So when we were done, the benzene was gone. And when we were done, we had 0.24 liters of oxygen. We figured out we could make 3.01 liters of carbon dioxide. There's only one thing missing, water. How much water is produced? Well, I know what the limiting reactant was. The limiting reactant was benzene. I know the molar mass of benzene. I can use my balance equation to find the ratio of benzene to water. It asks for how much, so I'm going to solve for it in mass. And I find that when this reaction is done, I have 1.21 grams of water. Limiting reactant problems. Okay. So, with a limiting reactant problem, you're always going to have one reactant is going to go away, but you're going to have to do the work multiple times, 2, 3, 4, 5 times, one time all the way through for every reactant. When you're done, you're going to compare all your products and pick the smallest. Don't add them up, pick the smallest. Last thing, last concept associated with this particular video, and that is the concept of percent yield. Percent yield is a grade. So if the problem were extended one step further and they were to say, wait a second, you said you could produce, and I guess that's the vocabulary here, you could produce, what does it take to get this thing to work? You could produce, let me go down here then. You could produce 3.01 liters of carbon dioxide. But you did the reaction. You actually did it because the 3.01 is a purely theoretical number. It's what you could do. And you did the reaction and you got 2.9. How'd you do? Well, percent yield is a grade. You take the experimental, which is the amount you really did produce, divided by the theoretical, how much you could have produced, and do the math. You find that this reaction was 96.3% effective, or there was a 96.3% yield. You created 96.3% of what you could produce. And that's the end of this video. So what we're going to do in our next 2 videos is we're actually going to spend a little more time on applications. We're going to look at some example problems of stoichiometry in the next video. And then the final video of this series, we're going to focus on a very, very special type of application, and that is the application of a combustion analysis. Until next time, stay safe. I will see you in synchronous, and toodles.